Okay, students. So let us do some problems. Yesterday we discussed Oswald dilution law. So let us do some problems related to that. So first one, determine the degree of ionization and pH of 0.05 molar ammonia solution. The ionization constant of ammonia is given 1.77 into 10 raised to minus 5 mole per liter. So now look at the, let me write the data, what are the data is given. Now they asked you to find the pH, they given the concentration, C is equal to 0.05 molar. That's the one data they given the concentration of ammonia. Remember, ammonia solution is basic in nature. And ionization constant, so you have to write Kb because now B stands for base. Kb is given, it is 1.77 into 10 raised to minus 5 mole per liter. So these are the data they given. You are asked to find the pH. What is the pH of the solution? So yesterday we discussed the theory. So let us apply it today. So now here now Kb is given, C is given. So first you can find alpha, the degree of ionization. Alpha, which is equal to root of Kb divided by C. Root of Kb divided by C will give you alpha. So what is Kb here? Kb is given 1.77 into 10 raised to minus 5 divided by C. C is given 0.05. So apply this equation. Yesterday we studied Kb is equal to C alpha square, where alpha is equal to root of Kb divided by C. So apply that equation, you're going to get alpha. Alpha means degree of ionization. So once you got alpha, you can move to the next step, because now yesterday we saw the concentration of OH minus, because this is a base. So here we talking about hydroxide ion concentration. So OH minus concentration will be C alpha, that we discussed yesterday. So C is equal to 0.05 and alpha is equal to alpha value that now we will obtain. If you do that calculation, that will be equal to 0.0354. Please do the calculation. So C into alpha, C into 0.0354 will give you the concentration of hydroxide ion. Will give you the concentration of hydroxide ion, which is equal to 0.00177 mole per liter. So that will be the concentration of hydroxide ion. Once you got the concentration of hydroxide ion, you can move to the next step. That is now POH you can find. POH will be equal to minus log concentration of hydroxide ion. So it is equal to minus log concentration of 0.00177. Apply here, take the negative logarithm of 0.00177. If you do that calculation, you will get POH. POH will be coming around 2.752. Once you got POH, yes, you can find the pH, because pH plus POH will be equal to 14. So pH will be 14 minus POH, which is equal to 14 minus 2.752, which will come around 11.248. Remember, this is actually a basic solution, so you have to get a pH which has to coming in the basic solution region. So now you can, that's the way you cannot check whether your calculation is right or not. So this almost looks good, because ammonia is now basic, so you are actually getting a pH which is coming around the basic region in the pH. Greater than 7, that is basic. Less than 7, that is acidic. Equal to pH equal to 7, that is neutral. Let us move to the next problem. Calculate the pH of 0.1 molar solution of a weak acid HA at 298 Kelvin. The Ka is given 4.9 into 10 raised to minus 8. So this time a weak acid. Now for a weak acid, we know what's the value they given. They given C. Concentration is given 0.1 molar. 0.1 molar concentration is given. The next data they given, now what is that? Ka. The next data they given, Ka is equal to 4.9 into 10 raised to minus 8. So these are the data they given. So from this data, what you need to find? You need to find the pH of the solution. Remember, this is an acidic solution. So if you do the calculation, you can ask the same way we did the previous problem. Alpha you first find, which will be equal to root Ka by C, which is equal to root of 4.9 into 10 raised to minus 8 divided by C, which is equal to 0.1. So that's the way you can find the alpha, degree of dissociation first. Then now once you got alpha will be coming around 7 into 10 raised to minus 4. 7 into 10 raised to minus 4. This is the degree of dissociation. So you got alpha. Once you got alpha, now this is we talking about acid. So concentration of hydronium ion. This time concentration of hydronium ion will be there in the solution, which will be equal to C alpha. Okay, which will be equal to C alpha. So C is already we know C is equal to 0.1. Alpha we got 7 into 10 raised to minus 4. So multiply that, you will get hydronium ion concentration. That will be coming around 7 into 10 raised to minus 5. 7 into 10 raised to minus 5 mole per liter. So having got hydronium ion, you can find the pH. pH is nothing but minus log concentration of hydronium ion, H3O plus, which will be equal to minus log concentration of 7 into 10 raised to minus 5. So apply this, you will get pH, you will get around 4.1549. Look at the pH values, definitely in the acidic region less than 7, but higher value. Higher value suggests it's a weak acid. For a strong acid, pH value will be very much less, like less than 1 or sometime less than 1. Okay, 0.1, 0.2, still strongly acidic. So that is the point you can remember related to how to find the pH of a weak acids and weak base. So we discussed the problem. Now let us move to the next most important theory. This theory, from this theory can I really expect a question for sure, because it's very important, that we call Debye-Huckel theory. Debye-Huckel theory. For strong electrolytes. Debye-Huckel theory for strong electrolytes. So we have in the previous theories, Arrhenius theory, we saw the problem is actually not working for a strong electrolyte. So we required some other theory for strong electrolyte. The behavior of strong electrolyte needed to explain specially. So because it's a different mechanism is going on in strong electrolytes. So that theory about a strong electrolyte has been explained in the Debye-Huckel theory. So it's some valuable points are there. This may be new to you, so you just understand one by one. So let us discuss the first one. Okay, the strong electrolytes are completely ionized in the solid state, and however the ions are not mobile in this state, hence they cannot conduct electricity. That's a very important point introduced in the Debye-Huckel theory. Okay, we know strong electrolytes do not conduct electricity in the solid state. So strong electrolytes do not conduct electricity in the solid states. Why so? Because they are strong electrolytes are, even though they are completely ionized, in the solid state. Even though they are completely ionized in the solid state, still they do not conduct electricity. Why? Because the ions means positive and negative charge ions are there. Yes, ions are formed, completely they are ionized, but the positive charge ion attract negative charge ion. So positive and negative charge ions are attracted each other, and ions cannot able to move to perform the conductivity. If you know, if you want to measure the conductance, ion has to move. The mobility of ion is very important. So mobility of ion is restricted when you talk about a solid electrolyte, strong electrolytes in the solid state. So that's the point. The mobility of ion, the mobility of ion, mobility of ion is restricted, due to intermolecular force of attraction. Intermolecular force of attraction. So the movement of ions is restricted due to the intermolecular force of attraction. That means yes, it cannot able to move as freely in the solid state, because it's always their attraction is there. Positive ion attract negative ion, negative ion attracts positive ion, so they cannot able to move. If they can able to move in a free manner, freely, then they can perform the conductivity. Here the movement is restricted. Ions cannot able to move, they cannot conduct electricity. That's why in the solid state strong electrolytes do not conduct electricity. Next one, when dissolved in a solvent, the ions are become mobile and are thus able to conduct electricity in the aqueous solution. So talking about now second point, talking about their conductivity in the aqueous solution. Why it's so? Because in the aqueous solutions ions have more space. They separates almost not completely, but still the ions have more degree of freedom of movement. The ions can move more freely in aqueous solution. Hence once they can able to move means they can conduct electricity. Hence they can conduct electricity. So that's an explanation why solid electrolyte, strong electrolyte do not conduct electricity in the solid state, because ions cannot able to move. Why strong electrolytes conduct electricity in the aqueous solution? Because now ions can move, because the movement of ions are can be performed in the liquid form, or we will say in the aqueous stage, because ions are more free to move between each other. The attractive force between the ion of oppositely charged determines the mobility of ion in a solution. But how this intrionic attraction affect the mobility of the ion? That two effects need to be considered: the relaxation effect and electrophoretic effect. Okay, so now this is the point you have to remember correctly. Even in the aqueous state, the strong electrolytes behaves differently depending on the concentration, because even in the aqueous solution the ionic attraction is there. Okay, so magnitude of ionic attraction between the positive charged ion and negative charged ion actually decide the movement of ion. So this is the most valuable point that brings in Debye-Huckel theory, where it's actually talking about an ionic atmosphere which exists in an aqueous solution in a strong electrolytes, which means a positively charged ions always symmetrically distributed by a negatively charged ions. Yes, negatively charged ions are there around a positively charged ion. Similarly, a negatively charged ions are surrounded by a positively charged ions. This is the way you actually see ions in an aqueous solution as well, which means always the attractive influence is there, because ions cannot able to move as freely as we expect in the ionic solution. It's not so. That why depending on the concentration the molar conductivity definitely varies, because it always depends how much attraction is there between the oppositely charged ion. For example, positive ions is surrounded by negatively charged ion, negative ions is surrounded by positively charged ion, which means they mutually attract each other, which are actually influencing their movement of movement of an ion that we can think. But here let us explain why different at a different concentration strong electrolytes have different conductivity, because at lower concentration, imagine a dilute solution, very high dilute solution. Now you can see as the dilution increases, the interionic force of attraction between the ions decreases, because they have more space to work it. Okay, ionic atmosphere is there, but distance between the ions will be less. Distance between the oppositely charged ion is less, means they have more freedom of movement. More they freely they can move, they can perform high conductivity. So that is the mechanism. Now you can talk about why, as the concentration decreases, as the dilution increases, molar conductivity increases, because the interionic force of attraction between the ions, oppositely charged ions, decreases. So there is a much better movement of ions, which means they conduct much better in a dilute solution. But you talk about not the lower molar conductivity at higher concentration. What will happen at higher concentration? At higher concentration, the ionic atmosphere is there, where positively charged ions attracts negatively charged ions, and there is a strong attraction between the oppositely charged ion exist in the solution. So which means they cannot able to move as we expect, because even in the aqueous solution this ionic atmosphere is there. So this ionic atmosphere we will call symmetric ionic atmosphere. What does it mean? Symmetric ionic atmosphere means one particular ion is surrounded by oppositely charged ions, which always influence their movement. So that kind of an ion, one positive charged ion surrounded by negatively charged ion, negatively charged ions symmetrically surrounded by positively charged ion. That atmosphere we will call ionic atmosphere. This ionic atmosphere is exist in the aqueous solution. Depending on how much ionic attraction is there between the ionic solution, that varies the molar conductivity. At higher concentration, this oppositely charged ions attracting more strongly, which means molar conductivity will less. And if you talk about at a very high dilute solution, oppositely charged ions attraction is very less, which means they can move much better or much in a free manner. The movement is more free considering in a aqueous solution. So that is a point related to the symmetrical atmosphere. Now let us discuss two more effects, because now it is observed that when electric field is applied, they actually have the conducting mechanism is there. They're showing much better conducting mechanism. For example, in previous class we discussed, when a sodium chloride dissolves in water, sodium ions definitely move to cation, moves to cathode, anion moves to anode. So that is there, existing there. But now why not this effect you cannot able to why this effect varies in the depending on the concentration of the solution. So let us take two important effects will come, and we call relaxation effect or asymmetric effect. Relaxation effect or asymmetric effects. So what is asymmetric effect or relaxation effect? This is something as the name suggests, the symmetry is lost when an electric field is applied. When an electric field is applied, the symmetrical effects of ions are disturbed, which means you have to understand before the electric field, one electric field was not there, then it was to charge ion symmetrically distributed by negatively charged ion. So there always a symmetry is there. The symmetry will be lost when electric field is applied, because positively charged ion tries to move to the negative electrode and negatively charged ion moves towards the positive electron. So symmetry will be lost in presence of an electric field. So there what will happen? There no, the positively charged ions try to move forward and negatively charged ion move backward if no a negative electrode is there. Imagine a negative electrode is there, a positive electrode is there, then no. So negatively charged ions, sorry, let it be positive here and negative here. A positively charged ion tries to move to the, sorry, positively charged ion tries to move to the negative electrode and negatively charged ion tries to move to the positive electrode. So this has to be positive. So there will be no a symmetry is losing because now they have a driving force to move because electric field is applied. So what that time will happen when electric field applied, you know, the symmetry will be lost. Now this time no, negative ion will be more no here than the positive ions, sorry, than the no, you talk about not different concentration of ions surrounding a particular ion. Talking about no, here positive ions, negative ions are symmetrically distributed. Here symmetry is lost. More negative ions will be on the back side of this particular ion and no, less negative ion on the front side. The symmetry actually lost. But still no, there is a dragging is there because no, negatively charged ions are here. So negatively charged ions will be on the back side, it always drags the movement because not allow the positive ions to move towards the negative electrode. They always have a dragging effect, retarding effect. That dragging effect or retarding effect we will call asymmetric effect or relaxation effect, which is a retarding effect influenced by a particular ion due to the presence of a oppositely charged ion, which is in the asymmetric atmosphere or asymmetric effect. So that we will call asymmetric effect or relaxation effect. So what's the point here? Oppositely charged ions always drags the movement of the other ion, which is this time negative ions are more on the back side, which means they always drags the movement. So which still retard the movement of a oppositely charged ion. That we will call asymmetric effect and symmetric effect. So asymmetric effect or relaxation effect. This relaxation effect what does it mean? Relaxation effect means let us discuss relaxation time here. Relaxation effect also called asymmetric effect. But relaxation time means once an electric field is applied, this symmetry is lost. The symmetry has gone, which means once symmetry is gone, it always takes time to rebuild the rebuild the symmetric atmosphere. It will take its time because symmetry is lost. It always takes its time to rebuild the symmetric atmosphere. So that that required time. So that not easy to rebuild that symmetric atmosphere in presence of an electric field. That point we will call relaxation time. Relaxation times. It's a time that's taken by the ions to rebuild the symmetric atmosphere. So that symmetric atmosphere cannot able to reach more easily, which means yes, because of that they do moves, but still the asymmetrical effect will be there, the retarding effect will be there due to the presence of oppositely charged ion which is present in the solution. So these asymmetrical effect also influence the conductivity. That why even though when electric field is applied, the molar conductivity exhibited by a particular electrolyte at a different concentration is different. A different electrolyte exhibit different molar conductivity at different concentration, and it always these factors like ionic atmosphere, asymmetric effect always have an effect. So that's the point student has to understand. We always finding an answer to why there are different molar conductivity based on different concentration. Why there is different molar conductivity different based on different electrolytes, because the magnitude of electrostatic force of attraction experienced by the oppositely charged ions have an effect in the molar conductivity. So that is a point really explained in the asymmetrical effect or relaxation effect. There are one more effect is there now that is more easy to understand once you understood this, that we will call electrophoretic effect. Electrophoretic effect. Electrophoretic effect. Now this is again you have to imagine just like an upper layer and lower layer. You can imagine like this, where upper layer moving in this direction, lower layer moving in this direction, means always there is a retardation in the movement of the upper layer, because everyone moving in the same direction, that always nice, that will increase the mobility. But one particular ion moving in this direction, oppositely charged ion moving in the opposite direction, which always retard the movement of a particular ion. So that retarding movement, that we will call electrophoretic effect. It is the retarding motion of a particular ion due to the influence of an oppositely charged ion which is present in the solution. We are talking about aqueous solution. So in a particular solution, the movement of one particular ion is influenced by, retarded by the presence of oppositely charged ion which is present in the solution. That dragging effect we can call electrophoretic effect. It is the electrophoretic effect. It is the retarding effect. Of a particular ion. The retarding effect of a particular ion is affected by the presence of oppositely charged ion. Presence of oppositely charged ion present in the solution. Which is moving in the opposite direction. So now you can remember these three effects which actually definitely going to affect the movement of ions in a solution. No, it's not that all the strong electrolyte behave in the same manner, because these kind of effects are definitely influence the movement of ions in a particular solution. Because now let us now summarize what are the three important effects. One is symmetrical ionic atmosphere. One positively charged ion is surrounded by symmetrically by the oppositely charged ion. That we will call symmetrical atmosphere. That means movement of an ions in a solution is always restricted in a solution. That's the point you can imagine. When there is talking about when electric field is not there, nothing is there, a positively charged ion is surrounded by negatively charged ion, that atmosphere is always there, okay, which always that force of attraction always need to break, or that has to be minimized for the free movement of ions. So remember the ionic atmosphere that always exists in the solution. Second point we call relaxation effect or asymmetric effect, which means when an electric field applied, we know when electric field is applied the electrolyte solution conduct electricity, because the ions are moving. A positively charged ion moves to the negative electron, negatively charged ion moves to the positive electron. But what will happen when an electric field is applied? The symmetry will be lost. The symmetry of a particular ion, the symmetrical atmosphere will be lost. Or positively charged ions influenced by negatively charged ions, and negatively charged ion also influence the positive charged ion. So what will happen? A positively charged ion moves towards the negative electron, negatively charged ion try to move to the positive electron, but still during that moment you can see a drag of one particular ion to the oppositely charged ion. Here negatively charged ion drags the movement, retard the movement of positively charged ion, because now this negative ion tries to attract the positive ion, because the concentration of negatively charged ions is more in the back side compared to front side. So the free movement is again restricted there. Now that effect that we will call a symmetrical effect. Okay, symmetrical effect, no, symmetrical effect where no ions are equally surrounded by positively charged ion. There also no, the movement is somehow restricted, but here no, you can see the influence will be more, because no, in negatively charged ion more in the back side, which now drags more compared to the symmetrical atmosphere. That's now even makes it more difficult. So how much concentration of negative ions is there, that always influence the movement of positively charged ion. That's the key point. How much the negatively charged ions is there in the back side, that influence the movement of positively charged ions. It's all depends so many factors. How much strongly attract, how much strong attraction is there between the oppositely charged ion. We're talking about electrostatic force of attraction between the oppositely charged ion, and the magnitude of the charge definitely influence. If it's now more negative, more positive, means now it will affect. And also remember, the concentration increases. Concentration increases means now the dragging effect will be more, because now it's more will be there, attraction will be there, more dragging effect will be there. That way, always at less concentration, the force of attraction between the oppositely charged ion will be less, which means the movement is more free. That way, always very dilute solution is good for a strong electrolytes to behave as a good molar conductors. Exhibit higher molar conductivity at the lower concentration or dilute solution. Next, electrophoretic effect. That is also very important effect, talking about the talking about movement of an ion. A positively charged ion is moving in a particular direction, where oppositely charged ions moving in the opposite direction. So always there is the retardation of movement is taking place. Now when you talk about a particular ion moving in this direction and oppositely charged ion moving in this opposite direction, so again that movement of ions is restricted by the presence of positively charged ion, which is moving in the opposite direction in the solution. So it's not an easy way the ions can move. That not dragging effect, the retarding effect of an ion, that we will call electrophoretic effect. So the if ions has to move, these kind of effects has to overcome. We're talking about symmetrical atmosphere is always plays a key role. Asymmetric effect plays a key role, and the electrophoretic effect plays a key role. So if these effects are, that's the way generally you can say, these effects are almost minimized in the dilute solution. Talking about very minimum electrophoretic effect, very minimum asymmetric effect, and symmetric atmosphere will be there, but no distance between the ions will be less, because more volume is there. So distance between the oppositely charged ion will be less, which means the electrostatic force of attraction between the oppositely charged ion will be less. So they have better movement in aqueous solution. So these are the factors that you can remember when you talk about the movement of ions of a strong electrolyte in a aqueous solution. So the next point, the slow and steady increase of molar conductance of strong electrolytes in a dilute solution due to the mobility of the ion gradually increases. So that we already told, right? Why molar conductivity increases on dilution? Because now at dilution, the electrostatic force of attraction between the oppositely charged ion is less, hence the movement of ion is faster in dilute solution. If ions can able to move faster, ionic mobility is faster, which means no molar conductivity will be higher. Next point, the mobility ions also depends on the frictional force offered by the viscosity of the medium and also dielectric constant and also temperature. So that's another effect talking about no molar conductivity of a strong electrolyte is also influenced by first one, viscosity of the medium. Talk about no viscosity of the aqueous medium. If no viscous force, the frictional force is higher, the movement is less. We always know required a medium which will have less frictional effect. So frictional force of the aqueous medium, viscosity. That's what viscosity is all about. Viscosity of the medium should be less so that no ions can move better, faster, exhibit higher molar conductivity. So viscosity of the medium definitely influence. Second point, no temperature. Temperature also an influence. Before that, no dielectric constant. Dielectric constant of the medium. We know dielectric constant of water is higher, which means no what the solvent actually do. Solvent actually allows more space between the oppositely charged ions. No, if you we discuss symmetric atmosphere where positively charged ion attract the negatively charged ion. If the positive and negative ions are closer, means no attraction is higher. So what the solvent actually doing? No, the distance between the oppositely charged ion become less in an aqueous solution. That why water has very high dielectric constant, which means no the water allows to separate the oppositely charged ion at a greater distance. So no ions will be more free. So if you talk about dielectric constant, water has very high dielectric constant, which allows no the oppositely charged ion to separate from each other much better compared to other solvent which having less dielectric constant. So dielectric constant higher means no ionic mobility will be higher, which means no molar conductivity will be higher. Next is temperature. Yes, temperature also plays a key role, because no temperature increases means ions having no more energy to move, right? So ionic mobility will be higher. That also helps at higher temperature. It also helps to break the force of attraction. Electrostatic force of attraction between the oppositely charged ion. So that will be always there. So higher the temperature, easier the movement of ion, ionic mobility is higher, molar conductivity will be higher. So that's the way now. So that sums up now almost the Debye-Huckel theory of strong electrolytes, which actually suggests the all kind of effects that we observe in the strong electrolytes. It's always influenced by some other factors. So please go through the today's portion, and next class we will discuss now Debye-Huckel Onsager equation. So this is a modified equation related to lambda m and lambda m 0, that is molar conductivity at infinite dilution, that we know that we will discuss in the next class on Sagar equation. Okay, thanks for listening. Let us find out.